Hello everyone, and welcome to our first lab activity here in general physics. Today I'd like to talk to you about scientific notation or exponential notation, followed by how to properly use a scientific calculator for the various scientific functions and scientific notation. And our last activity will be to use the calculator to make some calculations and ultimately plot a graph of position versus time so that we can get the slope of that graph and determine the velocity. Determining the slope of a graph is going to be a very important activity during these lab sessions. First of all, let's talk about scientific notation. This is also known as exponential notation. Either one is fine. Or it's also known as powers of 10 notation. Whoops. They are all the same thing. And we have to use this notation in not only in physics but in all of the sciences because the quantities that we measure occur in extremely large systems such as the universe or a galaxy, and they also occur in very tiny systems such as an atom or the nucleus of the atom. No matter what system of units we use, we wind up having to express very large numbers and very small numbers. And that means writing lots of zeros before we get to the decimal point, whether it's a large number or a small number. Scientific notation eliminates that and makes it much easier. The goal is quite simple. Since all of the numbers such as 1, 10, 100,000, 100,000, a million, a billion, and so forth can be written as exponents above a base. So for instance, 10 cubed is equal to 1,000, 10 to the 6th is a million, and so forth. We can write any number as a number between 1 and 10 multiplying a power of 10. Now, strictly speaking, you don't have to write the number between 1 and 10. But that is what is called standard notation. So a number such as 1.832 times 10 to the 6th is in standard form. This can be any number you want, and this can be any power of 10 that you want. But in standard form, where the number here, which is known as the mantissa, when the mantissa is written between 1 and 10, we can draw some conclusions about the final number. Specifically, if the exponent is positive when it's in standard form, the number is larger than 10. If it is 10 to the 0, of course, this is 1, and the number is equal to the mantissa. It's real easy. If the exponent is negative, regardless of what size it is, then the final number is less than 1. So one of the things about scientific notation it's important to get straight is that when you put it into standard form, which is a number between 1 and 10, multiplying a power of 10, then in this case, if the exponent is negative, the actual number is less than 1. If the exponent is 0, it's equal to the mantissa, and if it is positive, then the number is larger than 10. That helps keep things straight. negative exponents less than 1, positive exponents greater than 10. A 0 exponent means it's equal to the mantissa. It's between 1 and 10. Any number can be written in this fashion. To write a number in scientific notation, you may have learned that you move this left, you move this right, and so forth, but it's actually quite easy. First, we write down the number. There's the number in standard notation. Note that for this one, the number is less than 1. This means that we're going to have a negative exponent. We know we're going to get a negative exponent. What we do is we move the decimal point in whatever direction is necessary to get a number between 1 and 10, keeping track of how many places we moved it. In this case, we need to move it 2 places. So we end up with 1.326 times 10, and then we know that this was less than 1, so we moved it 2 places. The number of places we moved it is the exponent, and since the number is less than 1, it is a negative exponent. If we have, let's say, if we have this number and we wish to convert this to scientific notation, then we again move the decimal point in whatever direction we have to in order to get a number between 1 and 10. In this case, you can see we must move it to the left. 1, 2, 3, 4, 5 places. We get 1.63582 times 10, and since this is larger than 10, it is a positive exponent. 1.632 blah 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 times 10 to the plus 5. If the number was 6.28, if we want to put this into scientific notation, then all we have to do, since this is between 1 and 10, we don't have to move the decimal point at all. We move it 0 places. In scientific notation, we can say that 628 is equal to 6.28 times 10 to the 0. We don't often use this. It's kind of a waste, but we do. When the numbers get very large and very small, that is when scientific notation becomes very, very useful. When we have something like this. In this case, we know we're going to get a negative exponent because it's less than 1. We move the decimal point 1, 2, 3, 4, 5, 6 places. It's less than 1, so we get 6.5 times 10 to the negative 1, 2, 3, 4, 5, 6 times 10 to the minus 6. 1, 2, 3, 4, 5, 6. Right. Okay? If we have something like 6.2, or let's not do it that way. If we have something like 536000000.1, like that, this is larger than 10, so we move this 1, 2, 3, 4, 5, 6, 7, 8, and we get 5.36. We've got to be careful here. 0, 2, 3, 4, 5, 6 zeros times 10, and we moved it 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th, like that. You do not drop significant figures when you convert numbers into scientific notation. So that if you had 632.0800, and you were going to convert that to scientific notation, these are significant digits. These are significant. So is this one. So I move the decimal point 2 places, and I get 6.320800. We keep these digits, and we moved it 2 places times 10 to the second power. What about converting back the other way? You just reverse the game, keeping in mind that a positive exponent must give a number larger than 10. That will help you. So, here we have 6.25 times 10 to the 15th. Let's try that. We want to convert this over into standard notation. The positive exponent means the number we get must be larger than 10. That tells us we need to move the decimal place to the right. We write down the mantissa, and then we move the decimal place the number of places indicated by the exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we fill all of these spaces in carefully with zeros, and then we eliminate the final decimal point, and there is the final number. And this very nicely demonstrates why we use scientific notation. I also want you to notice something. The number of zeros is not the exponent. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros here, but the exponent is 15. Don't try and make the number of zeros match up with the exponent. What if we have a very small number? Suppose we have 8.760 times 10 to the minus 9th. Now we must keep in mind this 0 is significant. We have to keep it. We write down the mantissa, and anticipating we're going to have to move the decimal point to the left because minus 9 means less than 1, so we have to get a very small number. We have to move to the left. We have to write our mantissa 8.760. We write it over here, and now we have to move the decimal place 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1. Notice we retain this 0 because it is significant. And just to make sure that we can see that decimal point, we can put an extra 0 there just to do that. Again, notice that this is 9, but there are 1, 2, 3, 4, 5, 6, 7, 8 zeros. So do not try and match up the number of zeros to the exponent. It is that simple. Just keep in mind that if the exponent is 0, let's actually do that as a last one. If I have 3.74 times 10 to the 0, well, how many places do I move the decimal point? None. I just eliminate that, and it's that simple. I didn't have to move it any number of places at all. Next, what we'll consider is how do you enter scientific numbers into a calculator and work with them. The electronic calculator is a wonderful invention. It's amazing that for $10, you can get a device that can calculate logarithms, inverse logarithms, sines, tangents, cosines, square roots, cube roots, whatever. Just an amazing device. And these are also set up to accept numbers in scientific notation. The question is, how do you enter and manipulate numbers in scientific notation that have a mantissa and that have an exponent? Now, the people that manufactured the calculator know this about scientific notation, and they have made it very easy for you to enter these numbers. My guess, though, is that more than half of you enter the numbers incorrectly into the calculator. One thing I will say at the outset is that you do not use the 10 to the x key. This is known as the anti-logarithm key. You do not use this for entering numbers in scientific notation. You do not use it. If you have, it might work, but then sometimes it might not, and that's not really the intent of the manufacturer to use that key. Instead, you should be able to find a key that's marked EXP or EE. Sometimes there's a key that's marked like that. The problem is that this is not standardized among manufacturers. So while you're watching this video, look at your calculator and identify the key that is used. This one has an EXP on it. This one has this key. Some of them might have the double E key, and other ones might have a times 10 to the x key. Now, what this tells the calculator is that when you press this button, this is the exponent key. See, the calculator internally pretty much manipulates numbers in scientific notation. When you enter a number into the calculator, it converts it into a mantissa and an exponent. And then it multiplies the mantissas, it takes care of the exponents, and then it spits out the result. When you enter a number into the calculator in scientific notation, what it wants is the exponent and the mantissa. Pressing this key, and there might even be variations on this, tells the calculator that the next thing you enter is going to be an exponent. So if you wanted to enter 6.38 times 10 to the 10th, and you should do this with your calculator while you're watching the video, the keystrokes that you enter here are 6, the decimal point, 3, 8, the exponent key, or whatever variation you have of that, and then 10, and then what I would like you to do is press the equals sign. This will force the calculator to display the result. Here again, different calculators display things differently. On my Casio calculator, if I enter this 6.38 exponent 10, what I get in the display, you probably can't see it there, is this is what I get. 6.38 and then a little 10. That does not mean 6.38 to the 10th power, which is what it looks like. It is a cheap way of making a display for displaying the answer in scientific notation. I don't ever want to see this on a piece of paper. You must translate this onto paper to read 6.38 times 10 to the 10th. Some calculators might actually display it. It just depends. Some might do it like that, which is great. Some calculators will put an E in there. And this is typically how a computer might print it out in a spreadsheet. Often in Excel or something, you might enter it in this form. That's great. The E obviously means exponent. Once again, if you are writing a paper, writing a summary, or you're doing calculations, I want you to put it in proper scientific notation. This is the form, thou shalt write it. Some of you are getting sloppy in using this form. Technically it's valid. I don't like it. I want it put in that form. There are still some other calculators that might display it as this. They'll put a space in there. Well, you better watch out for that. That doesn't mean that a digit has gone bad on you. That's their way of expressing this number. The space means that this is the power of 10. This is the mantissa, and this is the exponent, okay? So you have to do it the correct way, all right? You must do it the correct way. Once again, you write it in this form. Now, how do you enter a negative exponent? You do not use the negative key, the subtract key. You do not use the subtraction key. You have to look for what is called the unary minus key. Okay? Or just the minus key, not the subtraction key. It, again, is different on different calculators. It might be marked plus/minus. That is how it is done on mine. It might be marked like this. And when you press that button, it puts in the minus sign, which effectively multiplies the number by -1. This is how you put in a negative number. So if you wanted to put in 6.38 times 10 to the -10th, the keystrokes for this would be 6.38 exponent key plus minus key 10, and then try hitting the equal sign to enter it. In that case, it may display like that, which means that. It might display like this. It might display like that. It might display like this. It is up to you to figure out on your calculator how to do these. The keys vary, but figure out which ones you've got. Sometimes you may have to push the shift or the second button on the calculator in order to get that function. To multiply numbers in scientific notation is no problem. You enter them just as I've shown you here, and multiply and divide and do whatever else, and the calculator will know exactly how to do it. So let us do 6.3 times 10 to the 6th times 8.2 3 times 10 to the minus 3. Now how do we do this? I'm going to show you the sequence here now. This would be entered as 6 decimal sign 3 exponent key 6 times 8 decimal 2 3 exponent key. You do not enter the times 10. Exponent key plus minus key 3, and then you hit equals. So let's all do that. Stop the video and do this right now. I do 6.38, I'm sorry, it's 6.3. 6.3 exponent 6 times 8 decimal 23 exponent plus minus key 3, and unless I goofed up, mine came out as 51,849. 51,849. Now I might have screwed up. I don't mind if I screw up in the video. So how do I know if I screwed up? You should do this with every calculation on your calculator. Type it in twice. If you get different numbers each time, you know you screwed up. So let's see what happens here. 6.3, clear, 6.3 exponent 6 times 8 decimal 23 exponent plus minus 3 equals, I get the same number. Now that doesn't guarantee that I have done it right, but if I get different numbers, I'm absolutely sure one of them was wrong and I got to do it again. Always, always type your calculations into your calculator twice to make sure you didn't mess up. Now if I want to put this in scientific notation, in some calculators you can actually push a button and it'll put it into scientific notation, but just as an exercise, this is a number larger than 10, so there's an implied decimal point there. I move it 1, 2, 3, 4 places. This is 5.1849 times 10 to the 4th. If I want to convert that to scientific notation. You multiply, divide, you manipulate numbers in scientific notation exactly the same as any other number, but you use the exponent key and possibly the plus minus key to enter negative exponents, and you multiply them, divide them, and manipulate them in exactly the same fashion as any other number. Alright, so next thing we'll do, let's take a look at how you use the other functions on the scientific calculator. Okay, we've talked about scientific notation, and we've talked about how to enter numbers in scientific notation into the calculator and how to manipulate them. How do you use some of the other functions in the calculator, such as sine, tangent, cosine, and so on and so forth? We can't cover everything. The ones that we're mostly interested in are the trigonometric functions, the sine, the cosine, and the tangent. Once again, the trouble is calculators are not standardized. They are not standardized. You should have the instruction manual for your calculator with you at all times so you can use it if you get confused. One of the difficulties with the sine and the cosine and tangent, the trigonometric functions, is that as we will see in this course, there are different ways of measuring angles. There are degrees, of course, which we'll often use, but later on we might use radians. Especially when we get to rotation, we will use radians. And there are also what are called gradients. 100 gradians equals a right angle. 90 degrees equals a right angle. Pi over 2 radians equals a right angle. They're all different, and there are conversions. We'll get to that in the class. But what you need to figure out is, by looking in your manual, you need to figure out how to change the degree mode of your calculator. Most calculators will have a little indicator. This one does right now. It has a DEG on it, which means it's in degree mode. If it says RAD, then it's in the wrong mode. Before you do any calculations involving sine, cosine, tangent, and any trigonometric functions, you have to be sure that your calculator is in the intended mode. One way to check, just to be sure, is to take the tangent of 45 degrees. And depending on your calculator, you may have to hit tan 45 and close a parenthesis equals to get the result. On the cheap calculators, you just type 45 and hit the tangent key. That's why I like the cheap calculators. They can use fewer keystrokes. So once again, on some calculators, you may have to hit TAN 45 close parentheses equal to get it. In other ones, you just type 45 and hit tan. Regardless, if you don't get 1, your calculator is in the wrong mode. If you take the tangent of 45 degrees and you don't get 1, it's not in degrees mode. All of your calculations are going to be wrong. If this is on an exam, all of your answers will be wrong, and they will be marked wrong. So learn to do this. How do you get it into degrees mode? You've got to look at your instruction manual. Some of them just have a trig button or a DEG button, and you just keep pressing it, and it cycles through the different ones. This one, you have to choose a mode and a number. Sometimes turning it off and turning it back on will force it back into degree mode. Regardless, figure out how to do it, know how to do it, and make sure it has been done whenever you start making calculations with degrees. Of course, if you're going to be using radians, be sure you set it in radians mode. You probably won't run into gradients. That tends to be an English thing, I think, okay, and an engineering thing, but you probably won't run into that. But degrees and radians, yes, okay? So for any of the trig functions, once you're sure it's in the correct mode, depending on the calculator, if you were actually going to take, say, the tangent of 30 degrees, on my calculator, the El Cheapo, you simply type 30 TAN and it goes. Boom. On some of them, you may have to write T, A, or you might have to put, push tan. So there may be, this is the tan button. In other ones, you put the tan button first and a parenthesis will come up. And then you put in the 30 and an equal sign and it finishes. You have to be sure that you know how to do it. This is also true for the sine and the cosine. Some calculators, you enter the angle first and then you push the sine, cosine, or tangent button. Other calculators, you put in the number first, like this one, and then you press the tan, cos, or sine button. It depends. Make sure you know what your calculator does. For square roots, there are, again, different calculators, and you will notice in the exercise today that there's a symbol. This is the square root symbol is this. This means the square root of 30. But in the handout, it's broken up a little bit, and it might look like that. I'll mention that later on. It's a word processor problem. Some word processor problems can't properly make a square root sign, and so you'll see in the handout, which I'll be talking about soon, that the square root sign is displayed a little bit strangely. For most of them, again, on a calculator like this, you simply enter in the number and then you hit the square root. Now on mine, I have to hunt for it. The square root sign is shift x squared. So some might have a little sign like this. Some might have an x squared symbol, and above it they'll have the square root. And to access this function, you must hit the second function and then hit the x squared, and that will give you the square root. That's how mine is, but they're all different. So I just hit shift and I get 5.477 something, 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 something. You have to study your calculator in order to understand how it works. Generally, beside the x squared, obviously the x squared key will square a number and so forth. Log keys, we'll get to those later on. We won't usually, but usually if you are okay with the powers of 10 keys and the sine, cosine, and tangent and square root keys, you are probably going to be okay as far as using your scientific calculator. But what you have to do is practice with a little bit, and that's what we'll do in the next section. Before we dive into the calculations we're going to do today, I want to show you a very important shortcut that can make life much easier with the scientific calculator. Also, it's not just part of the shortcut, but if you don't use it, you can get incorrect results. What we find very often, particularly when converting units, is we will get a calculation like this. Alright? We'll have to multiply a bunch of stuff in the numerator and then divide by a bunch of stuff in the denominator. Now I know a lot of you are going to do this in the following way, and it is valid and it works. One way to do this is to multiply the top, and I'm going to do it this way. 6 times 8 times 6 equals, I got 288. And then I multiply the bottom. 10 times 6.2 times 5 times 8, and I got 2480. And now I type these back in, and I get 288 divided by 2480. And I get 0.16 1 and some other things there. I'm not worried about significant figures at the moment. This is valid. This is valid. And this will work. But you're taking a chance. The problem here is that you are copying this from the calculator and you could make a mistake. You are doing this and copying it here and you could make a mistake. Then you are entering this back in, divided by this, you can make a mistake there. The probability of making a mistake is very, very high. Switching digits, leaving something out, very high probability. And it's a lot of work. The easy way to do this is to use parentheses. To rewrite this, if you have something like this, before you start to enter it, you put parentheses around the top and parentheses around the bottom. So if I do this now, I do not have to do any copying. What I do is I enter the left parenthesis, and then I enter 6 times 8 times 6. Then I enter the right parenthesis, and it just calculated this, and I don't copy it. Now I hit divided by, and then this parenthesis, 10 times 6 decimal 2 times 5 times 8, close the parenthesis. Now I have this, and then I hit it with a final equals sign. And I hit a final equals sign, and I get exactly the same number without copying anything out of the calculator and without putting anything back in. Once again, when you have several numbers on the top multiplying and several numbers on the bottom, put parentheses around the numerator and the denominator, and then the keying sequence is left parenthesis, 6 times 8 times 6, close parenthesis, hit the divide key, enter the next parenthesis key, 10 times 6.2 times 5 times 8, close parenthesis, and then don't forget to hit the equals key. This is much more efficient and much safer and much less likely to have an entry error than is the method that you have been using. Many times when we make measurements, we make more than one measurement. Or we make several measurements, average them together, and come up with an average, and then we want to compare that average to some sort of reference value. Or we may have two measurements that we've made, and we want to know how they compare to each other. Well, we can simply subtract the two values and say what's the difference between them and take the absolute value of that. But usually what we want to know is the percent relative error or percent deviation. We often call this the PRE. Sometimes it's also called the percent relative deviation. It's called an error when we have some truly accurate value for something and we want to know how we did compare to that. So we call it the percent relative error. But sometimes we have just two times we measured something, they're not the same, and we want to say, what is the percent difference between the two of them? It's usually the percentage difference that we are interested in rather than the absolute difference or the absolute deviation or absolute error. The percent relative error is easy to calculate, but there is a bugaboo you have to be careful about. The percent relative or the percent difference or percent deviation of A with respect to B is given by the following. When I say with respect to, this is the one I'm taking as the reference value. And technically, this is done by taking A and subtracting from it B. This will give a positive number if A is above B, and a negative number if it's below B. Then you divide by B. This and this, the variable subtracted off, should be the same as the one in the denominator, and then you multiply that by 100%. If you want the deviation of B with respect to A, you flip this and you change this to A. So the deviation of B with respect to A would be B minus A over A. It makes a difference, and it's not the same. It turns out if A is 10% above B, B is not necessarily 10% below A. There's a slight difference because of the change in the variable down here in the denominator. So be very careful about that. So if I have a measurement A is 10.6 meters and measurement B is 10.2 meters, and I want to know the deviation or percent difference between A and B, then we take A minus B, 10.6 meters, minus 10.2 meters, all divided by 10.2 meters, and strictly speaking, to be absolutely sure, you should put parentheses around that. If you don't include those parentheses, depending on your calculator, you might get an incorrect result, and then we multiply this by 100%. And so if we do this, we take 10.6 minus 10.2, and when I close the parentheses I get 0.2. Then I divide that by 10.2 and I multiply by 100, and I get about 1.96%, or approximately 2%. Percent deviations should be reported to no more than two significant figures. If you round 1.96%, which is what I got, to two significant figures, it's actually 2 or 2.0. 2%. Now let's just, for the heck of it, this is the deviation of A with respect to B. If I do B with respect to A, then I get 10.2 minus 10.6, all divided by 10.6 meters. Notice the change down here. With respect to A means A goes here and A goes here. Whoops, and we multiply that. Don't forget to write in the times 100%. You must include that to be mathematically correct. And in this case, 10.2 minus 10.6 is I think, did I do the other one correctly? Well, let's see, 10.2 minus 10.6, got to clear this, 10.2 minus 10.6 equals, divided by, and in this case I get negative 3.7% or negative 3.8%. And I think I made a mistake here. Let's do this again. Let me do that again. Here in the video I'm trying to rush. 10.6 minus 10.2. I think I did that incorrectly. Yep, it's 3.9. Yep, I made a mistake and I don't mind you seeing it. Notice that one is negative and one is positive, and they're not exactly the same. So I was rushing here in the video, and sure enough, when I entered this, I probably entered this number wrong, and I got the wrong answer there. So when you're doing your work, you have plenty of time, you enter everything twice, and you make sure that you get it correct. So one of the things we will often do in a lab is to calculate the percent difference between the lab value that we got and a reference value, or we might calculate something and do an experiment two different ways, get two different results, and want to know what's the percent difference between them. This is how you do it. Okay? Many times we will want to make a graph of our data, and eventually, if it's a linear graph, determine its slope. The hard part about making a graph is determining what to use for the coordinate axes. Typically, you will have a rectangular piece of paper, and you have to decide whether you want to do it in what we call portrait format or whether you want to do it in landscape format. Typically, that is up to you. But the rule that I like you to use when determining the format to use and the scale to use on each axis is you want your final graph to occupy at least half of the paper vertically and at least half of the paper horizontally. Okay? So that if your graph, if we quadrant these, as long as the graph extends outside, a graph like this is not acceptable because it's only on the left half. In this case, you would want it to go at least out somehow into the other section. So if it's at least half vertically and horizontally, you're okay. This would also be okay if it were a vertical type graph. If it just perhaps went to there, that's fine. But if it only occupies less than half vertically or horizontally, then you can change the scale so that it utilizes more of the paper. Likewise, if you're using the landscape mode, it should be more than half this way and more than half this way. So if your data is like that, it's fine. But if your data only occupies something like that, you've wasted this portion of the paper. If it only occupies something like this, you've wasted half of the paper. Ideally, you want it to at least cover more than half, vertically and horizontally. Of course, it doesn't have to be straight either. All right. Now, when you choose what each little box should be, whether vertically or horizontally, you don't want to magically choose some crazy value that will make it occupy the full width and the full height. You're going to usually have to be able to read coordinates on this graph, and if you choose a crazy coordinate system, you're going to have a devil of a time reading the coordinates. So generally, what I like to tell folks is that the increments in each little box should be 2, say 1, 2, or 5 times a power of 2, of 10. So that if each little box is 0.1, if each little box is 1, if each little box is 10, 20, 30, 40, 50, etc. Or if the boxes are 0.02, or 0.2, or 2, or 20, or something like that, that's typically acceptable too. Also, something like 0.005, or 0.05, or 5, 50. These are 5 times, say 5,000. These are 5 times a power of 10. 2 times a power of 10. 1 times a power of 10. You shouldn't have them going 0.3, 0.6, 0.9, 1.2. No. They shouldn't go 7, 14, 21, 28. Those are crazy. In some cases, I will accept multiples of 25. So things like 0.025, 0.05, or 25, 50, 75, 100, and so forth, where the multiple, where the increment is 25 times the power of 10, you could say that. That is marginal. Okay, that is marginal. Usually you can choose something like this. But 0.3, 0.4 per little square, 40, 80, 100, no, you should not do that. Choose the interval so that if I were to go up to your graph and pick a point on your graph, and I said, what are the coordinates of that point? If you have difficulty figuring out those coordinates of that point, then you haven't got a good choice of coordinate axes. And that's a bad graph. When you do make a graph, every graph, whether it be vertical or horizontal, should have a title. The title is typically the vertical quantity versus the horizontal quantity. So this might be, for instance, a graph of position versus time. Okay? There should be a title on the graph. There should be a label on each axis, and also the units that are going to be on that axis should be there. The bottom axis should have a label, and it should have the units that are being used. You should never have to refer to text or somehow refer to writing to figure out what the coordinates are. You should only have to look at the graph. When you plot your points, you can carefully plot the points. Now, depending on the experiment, they may or may not form a straight line. But let's suppose that they do form a straight line. You carefully plot your points. That's reasonable there. You carefully plot your points. And then, so that you don't lose the points, you circle them with a small circle to offset them so that you can see them easily. Like that. If you're going to determine the slope of the line, you're going to need to draw a best fit line. Now, I don't have a ruler here with me where I'm producing the video, so I'm going to have to do this by hand. But you always use a clear, see-through ruler. You should go and buy a clear, see-through ruler. Okay? What you need to do, this is reasonably straight. I've made a little bit of a mistake there, but in real life, your real data may be offset a little bit. Let me muck this up a little bit more so that it's more realistic. Let's try that, and then maybe that, and then maybe that. So you won't always get a perfect straight line with data. That's because of experimental error. But typically, after we've drawn the graph, again, title, coordinates on both axes and units on both axes. If it is a straight line, or if it's supposed to be a straight line, or if it looks like a straight line, you want to fit it with the best fit line. Now, if the data is curving, you don't try and fit a straight line to that. You don't you don't try and fit a straight line to that. Don't do that. Typically, experiments are constructed so that the quantities that we are looking for are the slope of the graph. It's possible to formulate the problem such that oftentimes a physical parameter, such as a velocity in this case, will be the slope of the graph. In this case, this is position and this is time. And if we want the velocity of this object, assuming that the velocity is not changing, and it doesn't look like it is because it doesn't look like the slope is changing, we want to determine the slope of a best fit line. When you draw a best fit line, what I always imagine are that these are pylons out in the ocean. We're looking down, we're going to lay a bridge on these, and the engineers have put down the pylons to the bridge, and then we're going to take a straight piece of pre-assembled roadway and fly it with several helicopters, and we're going to take that piece of roadway, which has a line down the middle, and we are going to then drop it on top of those pylons. We want to balance it as best we can across those pylons. When we have set that roadway down and balanced it as best as possible, the center line of the road is the best fit line. So you will want some points to be above the line, some will be below the line, some could be on the line, might be, might not, but you draw the line with a ruler in a single stroke, and you draw that line not just through the data points, but all the way across the graph paper. And do not force the line to go through the origin. It may not. The intercept of the best fit line may not be 0, and you should not force it to go through the origin. It may not. You want the line that best balances on all of these. Now I'm going to do it by hand, but you must use a ruler. Now in this case you can see this one's a little high, and so if I do this by hand, it might be something like that. Well, that's not good. It should be actually straight. But you understand what I mean. Some of the points will be above and below it. I'll tell you what I'll do. I'll go it backwards for the purposes of the instruction. And then I'll have some points might be above, below, right on. It's hard to say, but a line like that best fits them. This is very important to get an eye. This one turns out it might go through the origin, but don't force that. And you should extend the line outside the data points. Okay? And this is what is called a linear regression. Now computers can do this. I don't want you to use a computer to do this. I want you to figure out the slope of that line so you get the idea of the concept of what that slope is. Once you have drawn the best fit line, you want to find its slope. First rule, when determining the slope of the line, thou shalt not use any data points. Even if they're directly on the line, you shouldn't do that. If you use data points, you actually calculate the slope of the line. Like if you use these two data points and you calculate the line between them, you're calculating the slope of that line, not the slope of the line you drew. This is an averaging process. It's a very sophisticated averaging process that subtracts out certain systematic errors. So you never use data points. What you have to do is choose a couple of slope points. So you plot your points. Make sure your graph is properly labeled. You draw the best fit line. Plot your points, draw your best fit line. Now you must find its slope. You must choose 2 points on the best fit line, these must be on the best fit line, that you can easily determine the coordinates for. Now they shouldn't be too close together. So you don't choose 2 points here. You want to try and choose them as far apart as possible. The further apart they are, the more accurate your slope will be. When you go to determine this, looking at the graph paper, which of course has a grid on it. I don't show the grid over there, but let us suppose we have our grid and the line goes like that. You need to choose points that the coordinates are easy to read. It may be, but it's unlikely, that the line goes through what I call a crossroads. If it goes directly through a crossroads, I mean really through it, if it misses by a small amount like this does in all these cases, you cannot use a crossroads. If it happens to go through a crossroads, you can use that point because then you can easily read the coordinates of that point. If not, then you can choose another point where you can estimate it. For instance, I'm looking at this right now, and I drew a pretty good line here. It looks like this one. Actually, it looks like this one here. This is about 1/4 of the way from this line to this line. So if I choose this point, you mark that point, mark the slope points with an X. Mark the slope points with an X and label the coordinates. And label the coordinates. Mark the slope points with an X and label the coordinates. So for here, I could choose this one. I can read the vertical coordinate exactly. You can always choose a slope point so that you can read the vertical or the horizontal coordinate exactly. Then you have to estimate the other coordinate. This one is about 1/4 the way between these two, so knowing what these two are, I can calculate what 1/4 that way is, and then I can put the horizontal coordinate goes first with units, and then the vertical coordinate goes second with units. And I don't know what the values are here, but this would be some, say, x value here for our right point and some t value for the left point if we were doing this graph. So maybe this point corresponded to here. So I label these coordinates, x right, I have this actually backwards. It should be t right and x right, because the horizontal coordinate goes first, the vertical coordinate goes second. You see, I just made that mistake. Don't you make that mistake, okay? So we'll fix this here. So this is t right and x right. Do not label the coordinates of all the other points. Do not label the coordinates of all the other points. Just the slope point. Maybe down here I find one, looks at this one. This one looks like I can read the vertical line here, the time exactly, and it looks like the x-coordinate is about 1/3 the way up between those two. So I could use my calculator to calculate the difference, divide it by 3, and figure out what that point is. And this is the time for a left point and the x-coordinate for a left point. So over here, perhaps it's, we'll make it down here. And then you label this. We have the time for the left point and the x-coordinate on this graph for the left point. And these labels, this might be 2 seconds and 5 meters. This might be 10 seconds and 20 meters. I don't know. It depends on the scale. But these coordinates have units. These are physical quantities, and these coordinates have units, and they must be labeled with units. These are not pure mathematical numbers. They are physical measurements, and so they must be labeled with units. All right? The hardest part of all of this is determining and reading your slope points. You must be very careful to read your slope points. That's where mistakes are made. Once you have your graph labeled with your slope points, not on the graph paper, but in the sample calculation area of your report, in your lab report, you calculate the rise. The rise of the graph, this is the rise between these two, is the difference between the vertical coordinates. In this case, it's the x right minus x left. That is the rise of that graph. You don't have to sketch this on your graph. I'm just doing this to show you. If I make a right triangle connecting those 2 points, this dimension right here is the rise. This coordinate minus this coordinate. The vertical coordinate difference is the rise. The run is this distance. The right, in this case, the right time, and the run is the time for the right point minus the time for the left point is the run. You should show this just like I have it here, but with numbers in here and with units in all of these places. You don't have no units here and suddenly units over here. Units go in, units come out. Units go in, units come out. Then the slope of the graph is equal to the rise divided by the run. So then you take your answer from here, bring it down to here, take this answer and put it down here. I prefer that you not take this divided by this. I prefer a separate calculation here, separate calculation here, separate calculation here. And this is the slope of the line on the graph. On this graph, because it's position versus time, the slope will be the velocity. If this were velocity versus time, the slope would be acceleration. If this were the force needed to extend a spring, and this were the extension of the spring, the slope would be the elastic constant of the spring, and so on and so forth. So review this section very carefully because we will do this many, many times throughout the coming year in both semesters. We will be drawing graphs, we will be plotting points. Sometimes there might be a curved graph. Well, in that case we won't do a best fit line, but if it's a straight line, we will almost always try to calculate the slope. The procedure: decide on the line that you could put on there and balance the best. With a single stroke and a long ruler, you draw the line, you pick 2 points, where you can always read a vertical or horizontal component, and then you can make a good estimate of the other one. Once in a great while, you might get a crossroads where you can read both of them exactly, but that's quite infrequently. You carefully read the coordinates of those two slope points. You don't have to draw in this triangle that I did. That's just for illustrative purposes. You don't have to do that. And then you calculate your rise, you calculate your run, and you calculate your slope, which is the rise over the run, on a separate page, not on the graph paper. Okay? So review this section carefully. It's one of the most important parts of this entire video. So finally, we get to the actual part of this exercise. This video has been full of very important educational information. Now it's time to do a lab activity. What I want you to do, there should be 3 handouts that you received. Treatment of data, which is, I call this the lab handout. It's got a couple of pieces of graph paper in it. Guess what you're going to do with those. It's also got what I call a data sheet. All right. In addition to that, you have quiz, and you also have a lab report sheet. What you're going to be turning in is this lab report sheet, the quiz, and your graph and the data sheet that you've worked out. These you can tear off from this particular handout. I suggest that you read through the treatment of data. It's kind of a summary of everything that I've talked about here. So read through that. But what you will find attached to that is, I'm going to tear these off, is a sheet right here. What I want you to do first of all is change this sheet. In future labs, if the video has different instructions from the handout sheet, you follow the video. If there are sections in the handout sheet that are not covered in the video, you don't do them. For instance, there are a couple of problems here that you do not have to do. Over here on this page, TI3, T13, don't do those problems. Don't do those problems. Don't do that. You don't have to do that. Instead, you do the quiz. Okay? That makes life a little bit easier. I gave you 2 pieces of graph paper so you can mess up and then reuse another one. I suggest that you do the graphs with pencil so that you can erase them. So what do I want you to do for this lab? Well, you take the data sheet, as I call it, which is in the lab handout there, and first of all, at the bottom you see a group of, let's see, these are called Y's, okay? And you see at the top some X's, X1, X2, X3, X4, X5. I want you to change the following. Change the X's to T's. I want to give this physical meaning. I want you to change all of those X's to T's. They're going to be times in seconds. These are going to be times in seconds. Then change the Y's to X's in meters. We're going to make this so we're going to wind up with a graph like this. I want you to change the X's here to T's, cross them out and change them to T1 through T5, and put seconds over here. I want these changed to X's, and I want those changed to meters. You perform the calculations that are given there and fill in the answers here. That'll give you the practice with the calculators to 2 decimal places. 2 decimal places. That's actually about 3 significant figures, but 2 decimal places for all of these. When you look at this, you will see that there's that funky square root sign for x4, which is going to become t4. There's that weird one, and that's the square root sign I was talking about earlier in the video. Otherwise, you should be able to handle these, and the numbers should go up steadily. Just to help you out, they should go up steadily. If they suddenly go down, you probably made a mistake. And when you do eventually make a graph of them, they should form an almost perfect straight line. If you wind up with a point when you go to plot it and it's way off the beam, you made a mistake in the calculation. Go back and redo it. They should be almost a straight line, but not perfectly a straight line. This is essentially your data. You don't have to show any sample calculations for this because you're simply going to attach this to the lab report sheet. Okay? So that's the part where you gain experience working with your calculator. So you fill this out, change the x's to t's, the y's to x's. Perform the calculations, and then in the lab report summary sheet here that you're going to turn in as well, you fill in the two columns there below. Write an introduction up here. What did you learn from this video? What are we trying to show here, and so forth? The question we're asking is, scientifically, is this object moving with constant velocity? That's our question. And what is that velocity? So the experimental part of this is, what is the velocity of this object if it's moving at constant velocity? I took the data, made up some combinations here that would give those numbers to give you practice with the calculator. But now you're going to plot those position and time values on a graph. If you get a straight line, it's moving at constant velocity. And the slope of that line will be the velocity. So perform the calculations, transfer them to the front here, and then make a graph of position versus time. Now, having done this, I have discovered that it seems to work better that you do it this way. That for this particular experiment, you put the paper this way. Okay, this way. And I believe, I think you put it that way. All right, I think I worked out that you did it that way. You can decide. I think if it's and I think if you use a value of 1 for each of the squares, try that and see how it works out. But I'm leaving it up to you. It's up to you to an extent. You want to do it vertically, horizontally. That's up to you. What I suggest you do is try it out and see what you think. Okay? I might be wrong on this. I want you to figure out how to really orient the paper. Okay? But once you do, carefully plot your points, put a little circle around them, draw your best fit line, and determine the slope. Now for this experiment, your rise will have units of meters. Meters equals meters. Your run will have units of seconds. Seconds. Your slope will have units of meters per second. And this, in this case, is equal to the velocity of the object in meters per second. Now, we know that the actual velocity measured very carefully is about 3.00 meters per second. And your slope, by the way, can be given to 2 decimals, which is actually about 3 significant figures. You can read this to 3 significant figures, 3, 3, and you calculate the actual the slope is the v from experiment. The actual velocity was set up to be exactly 3.00 meters per second. So you can calculate the relative deviation, the percent relative error is the slope of your graph minus the reference value divided by the reference value times 100%. Now this isn't going to be exact because you're going to have some error and so forth. The big place to watch for is reading your slope points. Okay? Now, you can see we want an introduction, and it should be about that long. What did you learn here? How are you going to apply what you learned to this activity and so forth? How are we going to determine the velocity of this object and determine if it was constant? Your summary of your data is here. Your sample calculations, well, they're not going to be that many probably because that's where your slope calculations are. You know, for this lab, you're not going to have a whole lot of sample calculations. And then you write your summary and conclusions down here at the bottom. How close were you? Discuss. Why didn't you get exactly a 0% deviation here? It's very, very unlikely you will. Or if you did, comment about certain things about why you think that turned out. Comment about where problems could come in and difficulties that you have. That's what you write here. Was it moving at constant velocity? Did you get a straight line? And so on and so forth. Then, either next Monday or Wednesday, depending on what section you're in, you turn in this page on the top with the graph. Well, you can actually have this page stapled to it and your graph stapled to it as well. And that is your lab report. Stapled, not paper clipped. If you've got any difficulties, go back through the video and take a look at them. There's a lot here. This is a lesson really combined with an activity that puts some of that together. But remember, our labs are 2.5 hours long, so total time you should be putting into this is at least that amount of time. Okay, take care.